Hello everyone. In continuation with the video lecture series on advanced calculus and numerical methods, subject code 18MAT21, today's session, that is lecture 4 on module 1 vector calculus, I will take vector integration, where we'll learn line integral, surface integral and volume integral, and also the interdependency between these three integrals, among which the Green's theorem I am going to discuss here. We start today's session with vector integration, in which the first one we take line integral. So far we have integrated over intervals, that is a definite integral of y equal to f of x between x equal to a and x equal to b, which gives the area under the curve y equal to f of x between the ordinates x equal to a and x equal to b. Similarly, we have taken integration over areas by means of double integrals or over volumes using triple integrals. So here the line integral is nothing but we are going to investigate the integration over or along a curve. Suppose let me say a vector field is applied in a region and C is a curve that is wandering through the vector field. That means at each point it takes the dot product of vector field F and the displacement vector at each point and summing up. So we are going to sum up. So that means we have approximated the line integral of f dot dr, where f is a vector point function and dr is nothing but tangent vector. So that's why it is called the tangential line integral of vector point function, where f is f1i plus f2j plus f3k. Along a curve C, we can write it as a line integral of f dot dr, or if I take the parameterization, that is r as a function of t, then f dot dr by dt we can also depict here. Suppose we have a vector field applied in the region and C is a curve along which we are taking the dot product of f and dr, where r is the equation of the curve in space and dr is nothing but dxi plus dyj plus dzk. So if f is f1i plus f2j plus f3k and dr is dxi plus dyj plus dzk, then the line integral I can write it as f1 dx dot product between these two. So f1 dx plus f2 dy plus f3 dz. So we can just take the equation of the curve C. Along C we are going to integrate this, so that becomes a simple real integral. So here one thing you can remember, so this is a path dependent, the integral is path dependent. So there are other types of line integrals, that is f cross dr and the integral f dr. So here we take the physical interpretation of line integral of f along C. Suppose if that vector field f represents the velocity of a fluid particle, then your line integral of f along C is nothing but the circulation of f around the curve. Suppose that circulation of f around every closed curve in the region E is 0, then f is irrotational in E. Now similarly, the one more interpretation is, if suppose f is nothing but a force acting on a particle which moves along an arc AB, then your line integral of f along C is nothing but total work done by f during the displacement from A to B. So that means it is work done carried in displacing the particle along that curve between A to B, from A to B. Now let me take some problems on line integral. The first one, if vector field f 3xyi minus y square j, evaluate line integral of f along C, where C is the curve in the xy plane y equal to 2x square. That is a parabola given here from 0, 0 to 1, 2. So here we have to first find the dot product between f and dr, which is nothing but dxi plus dyj, because r is xi plus yj, since it is in xy plane z equal to 0. So once you get the dot product, then you can evaluate along the curve y equal to 2x square between the point 0, 0 to 1, 2. So in xy plane, obviously z equal to 0, dz is 0. So vector point function is here 3xyi minus y square j, and dr is dxi plus dyj. So take the dot product. First simplify this. That gives a sum of the product of components, that is 3xy dx plus minus y square into dy means minus y square dy. Now once it is taken, so you have to evaluate along the curve y equal to 2x square. The path here is y equal to 2x square, means dy is derivative of x square is 2x dx into 2 4x dx. So substitute over here. So y becomes 2x square and your dy is 4x dx. If I substitute that, 3x into 2x square 6x cube, y square into 4x dx, that is y square is 2x square the whole square, that gives 4x power 4 into dy, that is 4x power 4 into 4x 16x power 5 dx. So I can write dx common. So this simplifies to, first you simplify the dot product between f and the displacement vector dr. So which now simply a function of x, means it is a simple real integral. So we need the limit for x now. So since it is 0 0 to 1 2, from this I can obtain the limit for x, that x varies from 0 to 1. So now it is simple. We can take the line integral f along c is nothing but now integral 0 to 1 6x cube minus 16x power 5. Just integrate this. Integral of x cube is x power 4 by 4. So 6x power 4 by 4 minus 16 into integral of x power 5 is x power 6 by 6. Apply the limit 0 to 1. Upper limit 1 minus lower limit 0. So that gives 6 by 4 minus 16 by 6. Simplify, you get minus 7 by 6. Similarly, the same problem one can ask in other way. In application oriented means they can ask, find the total work done by the force 3xyi minus y square j in bringing the particle along the curve y equal to 2x square from this point to this point. The answer is same, because the line integral of f along c, if f represent the force applied in bringing the particle from one point to other along the given curve, that means it is total work done. Second problem, find the work done in moving a particle by the force F equal to 3x square I plus 2xz minus yj plus zk along. Here we have two curves. The first one is a straight line from 0 0 0 to 2 1 3, and the second curve is defined by x square equal to 4y 3x cube equal to 8z from x equal to 0 to x equal to 2. So here we have to find work done in moving a particle by this force field along some curve between the given points. So that means it is nothing but finding line integral of f along that given curve. So f is 3x square I plus 2xz minus yj plus zk, but along the straight line, the equation of the curve is not given directly here. Instead, we know that it passes through 2 points. So by using 2-point form, we can write that is x minus x1 by x2 minus x1 equal to y minus y1 by y2 minus y1 equal to z minus z1 by z2 minus z1. Equation of the straight line passing through the points x1, y1, z1, x2, y2, z2. So by substituting, we get x minus 0 by 2 minus 0, that is x by 2 equal to y minus 0 by 1 minus 0, that is y by 1 equal to z minus 0 by 3 minus 0, that is z by 3. So they are equal to say some parameter t, so which gives x equal to 2t, y equal to t, z equal to 3t. So we can now take dot product means f dot dr, that is in terms of dx, dy, dz. So we can convert, because x, y, z as a function of t, which implies now dx, dy, dz is nothing but dx is 2 dt, dy is dt, dz is 3 dt. So take the dot product f dot dr, that is 3x square dx plus 2xz minus y dy plus z dz. As you know, dr is dxi plus dyj plus dzk. Now substitute everything as a function of t here. So x equal to 2t, y equal to t, z equal to 3t. and corresponding dx, dy, dt in terms of t. So carefully substitute. If I substitute, it gives 3x square, that is 2t the whole square, 4t square into 3, 12t square into dx, that is 2 dt, 24t square dt. So I have first term 24t square. Similarly, 2xz minus y dy. Substitute x equal to 2t, z equal to 3t. So that gives a 2 into 3, 6t square into 2, 12t square into dy, that is dt. So I have 12t square dt minus y dy. So y is t, dy is dt. So that's why it is minus t dt plus z dz. Z is 3t here, dz is 3 dt. 3 into 3, 9t dt. So I have simplified. Finally, 24t square plus 12t square is equal to 36t square minus t plus 9t, that gives 8t. So which I can now integrate. The line integral now becomes a simple real function of t, integral of real function of t. So I want corresponding t limits. So as I know x equal to 2t and x varies from 0 to 2, so that means when x equal to 0, t equal to 0 by 2, that is 0. When x equal to 2, t is 2 by 2, that is 1. So that means corresponding to x equal to 0 to 2, t becomes 0 to 1. So I get the limit for t is 0 to 1. If you use any relation y equal to t and corresponding y limit, that is 0 to 1, you will get the same limit. So even if you take z equal to 3t and z varies from 0 to 3, you will get t equal to 0 to 1. T varies from 0 to 1. So your line integral, that is nothing but work done, which is nothing but line integral of f along c, is the integral of 36t square plus 8t between the limit 0 to 1. So integrate this now. So integral of t square is t cube by 3. So I have 12t cube plus 8t square by 2, that is 4t square. Apply the limit, upper limit 1 minus lower limit 0. So that gives 12 plus 4, 16. So the total work done in bringing a particle along the straight line from the point 0, 0, 0 to 2, 1, 3 with the help of this force is 16 units. So 16 joule. So next we need to find the work done by the same force, that is F equal to 3x square I plus 2xz minus yj plus zk, but along the curve x square equal to 4y, 3x cube equal to 8z between the point x equal to 0 to x equal to 2. So that means here already we got f dot dr. Now I write the equation of the curve. So in terms of x, so by this y is equal to x square by 4, z is equal to 3x cube by 8. So I can get dy and dz. Dy is 2x dx by 4 gives x by 2 dx. Dz, differentiate this, that is a 3 into 3x square dx by 8, 9x square dx by 8. So substituting in your f dot dr, which I got 3x square dx plus 2xz minus y dy plus z dz. Now I can substitute y as x square by 4, z as 3x cube by 8, followed by dy and dz in terms of x already we have here. So after substituting, so I get it is a function of x as 3x square plus 51 x power 5 by 64 minus x cube by 8. Substitute carefully and simplify. You will get f dot dr as 3x square plus 51 x power 5 by 64 minus x cube by 8. So the work done, nothing but the line integral of f along c is now it is integral of 3x square plus 51 x power 5 by 64 minus x cube by 8 corresponding with respect to x. So that's why limits are here already given, x from 0 to 2. So integral of this is 3x cube by 3 x cube plus 51 x power 6 by 6. So I have 17 x power 6 by 128 minus x power 4 by 4 into 8 x power 4 by 32. Apply the limit, upper limit minus lower limit. So after simplifying, you will get the work done by the force 3x square I plus 2xz minus yj plus zk in moving a particle along this curve from x equal to 0 to x equal to 2 is 16. Problem number 3. Find the work done in moving a particle by the force F equal to 3x square minus 6y zi plus 2y plus 3x zj plus 1 minus 10x yz square k along a straight line from 0, 0, 0 to 1, 1, 1. Here also we need to find work done. That means the line integral of f along the curve, and the curve is a straight line joining these 2 points. So let me take first the equation of the curve, that is a straight line passing through the point 0, 0, 0 and 1, 1, 1 using 2-point form. That gives x minus x1 by x2 minus x1. So x1 y1 z1, x2 y2 z2 are here. So x minus 0 by 1 minus 0, that is x by 1. Similarly, we have y by 1 equal to z by 1 equal to say some parameter t. So I get x equal to t, y equal to t, z equal to t is the parametric equation of the given straight line joining these 2 points. Thereby dx, dy, dz is nothing but dt. Dx equal to dt, dy equal to dt, dz equal to dt. Now let me take the dot product between f and dr, where f is given here 3x square minus 6yzi plus 2y plus 3xzj plus 1 minus 10xyz square k, where dr all you know, that is dxi plus dyj plus dzk. Dot product is now 3x square minus 6yz dx plus 2y plus 3xz dy plus 1 minus 10xyz square dz. Substitute in terms of t now, x equal to t, y equal to t, z equal to t, dx dy dz becomes dt here. So I can carefully substitute, which gives now 3t square minus 6t into t, 6t square dt. So I have 3t square minus 6t square dt. So dt is common, taken out. 2t plus 3t into t, that is 3t square, 2t plus 3t square plus 1 minus 10t into t square, t power 4 minus 10 t power 4. After simplifying, you can see that 3t square plus 3t square, 6t square cancel with this minus 6t square gives a minus 10 t power 4 plus 2t plus 1. So we can now say the dot product between f and dr is nothing but a function of t. So we have to integrate with respect to t, means corresponding limit for t I want. So where x equal to t and x varies from 0 to 1. So I can say t is also varies from 0 to 1. So work done is nothing but the line integral of f along c. Now f dot dr is minus 10 t power 4 plus 2t plus 1. So integrate with respect to t between the limit t equal to 0 to 1. So integral of this is minus 10 t power 5 by 5 gives minus 2 t power 5 plus integral of 2t, t square by 2, 2 gets cancelled, that is t square plus integral of 1 is t. Apply the limit, upper limit minus 2 plus 1 plus 1. So that is minus 2 plus 2 gets cancelled. Lower limit anyhow gives 0. So the work done in moving a particle by this force field along the straight line between the point 0, 0, 0 to 1, 1, 1 is 0 units. Next, I take problem number 4. A vector field is given by vector f equal to sin yi plus x into 1 plus cos yj. Evaluate the line integral over a circular path given by x square plus y square equal to a square, z equal to 0. So here I want to find the line integral of f along the circular path, that is x square plus y square equal to a square. Instead of taking with respect to x or with respect to y, it is better to take in terms of parametric form. As all of you know, the parametric equation of x square plus y square equal to a square is x equal to a cos t, y equal to a sin t. Thereby dx and dy, dx is minus a sin t dt and dy is a cos t dt. For a circle, t varies from 0 to 2 pi. So 0 less than or equal to t less than or equal to 2 pi. Now let me take the dot product between f and dr, where dr is dxi plus dyj, because z is 0 means dz is 0. This is on plane. So f is already given, sin yi plus x into 1 plus cos yj dot dr dxi plus dyj. The dot product is nothing but sin y dx plus x into 1 plus cos y dy. Now substitute carefully in terms of t. So what I get? Sin of y, that is a sin t, sin of a sin t into dx, that is minus a sin t into sin of a sin t dt plus x is a cos t into dy is anyhow a cos t dt. So together it gives a square cos square t dt into 1 plus cos of a sin t. So that is what I have written here. So f dot dr now finally gives minus a sin t into sin of a sin t plus a square cos square t into 1 plus cos of a sin t dt. So now we have to integrate this between the limit 0 to 2 pi. So before integrating, let me just observe. So the terms are now, I can separate the terms. One is a square cos square t into dt. So I can integrate this very easily by using the reduction formula. The left out terms are here, minus a sin t sin of a sin t plus a square cos square t into cos of a sin t dt. See, if I observe this second and third term together, so this is a direct derivative of product of two terms. among which one is sine of a sine t. If I take that as a one term, its derivative comes here. So that is cos of a sine t. Derivative of sine of a sine t is cos of a sine t into inner term. Derivative is a cos t. So which I have already here a cos t. The another extra is a cos t. So I can take the one term is sine of a sine t. Another term is a cos t. Its derivative lies here already. That is minus a sine t. So that means this together I can write the derivative of product of a cos t and sine of a sine t. So I have the second term also. Now integration now becomes easy, because if I integrate that with respect to t, integral and derivative gets cancelled. So which I can integrate. Therefore the line integral of f along c now becomes a square cos square t plus derivative of a cos t into sine of a sine t between the limit 0 to 2 pi. Correct? Between the limit 0 to 2 pi. So with respect to t. So I can split that two integrals. One is integral 0 to 2 pi a square cos square t dt. Another is d of a cos t sine of a sine t. So we have to integrate. So this integral is straight away we get a cos t, because integral and derivative gets cancelled. So the answer is a cos t sine of a sine t, but apply the limit 0 to 2 pi. But how we can solve this, students? So we can use the reduction formula. For that I need integral should be under the definite limit 0 to pi by 2. So I can use the nature. So here it is under 0 to 2 pi. This is an even function, because cos of 2 pi minus t is cos t. So cos square 2 pi minus t is cos square t only. So I can write 2 times 0 to pi. Again under 0 to pi cos square t, again it is even, because cos of pi minus t, though it is minus cos t, since we have even power it gives cos square t only. So again 2 times. So earlier 2 times gives 2 times 0 to pi, and again integral 0 to pi gives 2 times integral 0 to pi by 2. Together it is 4 times integral 0 to pi by 2. So this now is a standard formula. So we can use the reduction formula to evaluate this. But here answer is already got a cos t sine of a sine t. Apply the limit t equal to 2 pi, but sine of 2 pi is 0. So that means everything becomes 0. Lower limit is anyhow 0, sine 0. So this anyhow gets cancelled. So only thing is I have to apply the reduction formula to get the answer of second. So which we know, integral 0 to pi by 2 cos power nx dx. So that is n minus 1 into n minus 3 etc. Denominator n into n minus 2 etc. End up with k, where k is pi by 2 if n is even, and 1 if n is odd. Here n is 2, that means it is 2 minus 1, that is 1 by n is 2 half times k. So k is now pi by 2, since 2 is even, so it gives pi by 4. Pi by 4 into 4a square. So 4 cancels, so it gives pi a square as the answer. Now after the line integral, let me take a surface integral. Instead of integrating the vector point function f over or along a curve C, here we are integrating over the surface S. So the surface integral, we can say the normal surface integral of f over the surface is given by integral of f over S, or it is integral of f dot n over S, where n is unit outward normal vector to the surface at the given point P. So that means I can say the surface integral of f, a vector point function over the surface S, is the integral of the component of f along normal to the surface. Correct? So that means if suppose a surface is given and a vector point function or vector field is applied over it, and what is n? So n is nothing but unit outward normal vector. So that means if I have n is the vector normal to the surface, and all of you know if f is a surface, given surface, here it is defined as S now. So gradient of S, the gradient is nothing but vector normal to the surface. I want unit outward n cap, we have denoted here as capital N, that's all. Unit outward normal, so that is vector normal to the surface by magnitude of that. So that gives n cap or capital N. So we have unit outward normals. Find the dot product between that f and unit outward normal and integrate over the surface. So if I want to find integral over the surface, obviously, so we have to get the projection of that on the xy plane, so that it is nothing but double integral. So finally it becomes a double integral. So we have to take the corresponding limit for x and y, which we can do either with respect to x first, y next, or with respect to y first, x next. The same I have taken here. Suppose this is the given surface, and at the point P the unit outward normal is n. So then I can evaluate the line integral of f over s, means it is integral of f dot n over the surface s. The other types of surface integrals are here f cross ds or integral of f ds. Now what is the significance, the meaning? If suppose your f, the vector field f, represents the velocity of a fluid particle, if it is the velocity of a fluid particle, then the total outward flux of f across a closed surface S, the total outward flux of this vector field, that is nothing but the velocity of a fluid particle across a closed surface S, is nothing but the surface integral of f over s. So that means if f represents the velocity of a fluid particle, then your surface integral of f over s means it is total outward flux of f across the closed surfaces. And in case if flux across every closed surface in a region is 0, then we can say f is a solenoidal vector. Similarly, now if I move on to volume integral, so that means if suppose f is a given vector f1i plus f2j plus f3k, suppose f is a vector point function, and v is the volume enclosed by that closed surface, and dv is an infinitesimally small element, or you can say the change in v, that is dx dy dz, then the volume integral of f over e is given by integral of f over e. So it is nothing but now triple integral. So we have to take triple integral of f1 dx dy dz component wise, we have to integrate that. So with respect to x y z, so corresponding limit of x y z we have to take. Now all of you are thorough with this triple integral concept, so we can integrate that. So that is f1 with respect to x y z, so f1i, so we have triple integral over the region E, f1 dx dy dz I plus triple integral of f2 dx dy dz j plus triple integral of f3 dx dy dz k. So we have to find the corresponding limit for x y z, so which we can further integrate, so which gives the volume integral of f over the volume that is enclosed by a closed surface. Yes, correct. So let me take some problems on surface integral. So instead of solving problems on surface integral and volume integral separately, so let me give the interdependency between these three integrals, that is line integral, surface integral and volume integral, by the theorems one by one. The first one is Green's theorem in the plane. So the Green's theorem is nothing but it relates your line integral around a closed curve C. If suppose you want to find the line integral of a vector field or vector point function defined in a plane, the line integral of f along a simple closed curve C in terms of a double integral over the region bounded by this closed curve. So that means obviously if you have a closed curve C, the path is now closed curve C, then it is bounded by some region R. So the line integral you can convert as a double integral over this region R. So usually what we have taken whenever we are taking the line integral, so f dot dr, we can take the dot product between the vector f and the displacement vector dr, where it is in the xy plane means dz is 0. So I have f1 dx plus f2 dy. We are going to evaluate, or we are going to integrate this f1 dx plus f2 dy along the given path or along the given curve C. But if it is a closed curve, instead of taking along that C, instead of that we can use the Green's theorem, which in turn gives a double integral over the region R. So let me take the statement of Green's theorem now. Here instead of f1 as a function of x comma y, f2 as a function of x comma y, I have taken m and n. So the statement goes like this way: if m of x comma y, n of x comma y, and its first order partial derivatives, that is m with respect to y, dou m by dou y and dou n by dou x, are continuous in a region R of the xy plane bounded by a closed curve C, then the line integral of m along C is nothing but now mdx plus ndy. We can say the integral mdx plus ndy over C is equal to double integral of, we can find the term here, that is a dou n by dou x, partially differentiate n with respect to x minus dou m by dou y. So integrate this fact over the region R with respect to x and y. So that means if I have a closed curve C bounded by the region R, so this is the region R bounded by this C, instead of evaluating along the curve C, I can take this dou n by dou x minus dou m by dou y by identifying m and n, differentiate partially with respect to m with respect to y, n with respect to x. So dou m by dou y and dou n by dou x, somewhere it is familiar. When we have taken exact differential equation, you know that the condition for exactness is dou m by dou y must be equal to dou n by dou x. So that same we have taken. So difference between this two partial derivatives, so integrate that over the region R means identify the limits corresponding to x and y. Either you can integrate first with respect to x, then y, or vice versa. So now whenever you are taking a line integral along a closed curve C by Green's theorem, we can take it as a double integral over the region R, where the function is nothing but dou n by dou x minus dou m by dou y. Correct? So let me take now some problems on Green's theorem. The first problem here we have the application of Green's theorem, so which we can use while finding the area enclosed by a plane curve. So that is given here. Apply Green's theorem to prove that the area enclosed by a plane curve C is nothing but half times integral of x dy minus y dx over C. So using this, thereby I can find the area of an ellipse whose semi-major and semi-minor axes are of lengths a and b. That means x square by a square plus y square by b square equal to 1. Now let me first take the statement of Green's theorem. As all of you know, the line integral of mdx plus n dy can be written as double integral over the region R, identify m and n, dou n by dou x minus dou m by dou y. So this factor you have to integrate over the region R by identifying the corresponding limit. So here what we have is integral of x dy minus y dx, where m is nothing but now minus y and n is x. Correct? If I take it as a mdx plus ndy form, so m is minus y and n is x. So dou n by dou x is nothing but 1, partially differentiate n with respect to x, that is 1, minus dou m by dou y, that is minus 1. So I can substitute here. So this line integral can be written by using Green's theorem as double integral over the region R, dou n by dou x, that is 1, minus dou m by dou y is minus 1, so which is nothing but 2. So I have just 2 times integral dx dy over the region R. So what this actually represents? So this represents area enclosed by that curve. Correct? So I can say now it is 2 times area enclosed by the plane curve C. So that means area enclosed by the plane curve C can be taken as half times integral x dy minus y dx. So this result I use for solving or finding area of an ellipse, x square by a square plus y square by b square equal to 1. So as you know, the area of an ellipse, a plane curve, a closed curve, we can find by using this result, half time integral of x dy minus y dx along the curve C, where by Green's theorem we have taken this result. But here, since we have an equation of ellipse, instead of integrating with respect to x or y, we can take the parametric equation of x square by a square plus y square by b square equal to 1, that is x equal to a cos t, y equal to b sin t. The parametric equation of circle is x equal to a cos t, y equal to a sin t. So here it is x equal to a cos t, y equal to b sin t, thereby dx dy I can get minus a sin t dt, and dy is b cos t dt, and for ellipse the t varies from 0 to 2 pi. Substitute here, which I get now x into dy, that is a cos t into b cos t dt, x dy, a square cos square t, sorry, a into b, ab cos square t dt. So I got ab cos square t dt minus y into dx, that is minus b sin t into dx is minus a sin t. So minus of minus plus ab sin square t. So I have ab is a constant, cos square plus sin square, then it is nothing but 1 cos square t plus sin square t. So I have ab by 2 integral of 1 with respect to t between 0 to 2 pi. So that is apply the integrate that 1, that is t, and apply the limit 2 pi minus 0, that is 2 pi into AB by 2 outside, so 2 gets cancelled. So the area of an ellipse is pi AB, as all of you know that. So by using this result also, I got the area of an ellipse is pi AB. The second problem here is, if C is the simple closed curve in xy plane not enclosing the origin, then show that the line integral of f along C is 0, where the vector field f is yi minus xj by x square plus y square. So let me first take what is f dot dr now, where f is now y by x square plus y square I minus x by x square plus y square j. On plane, that's why dr is dxi plus dyj. The dot product gives y dx by x square plus y square minus x dy by x square plus y square. So that means the line integral f dot dr is nothing but integral of y dx by x square plus y square minus x dy by x square plus y square. So here, since it is a simple closed curve, so I can use Green's theorem, where m dx plus n dy, the line integral of m dx plus n dy, I can convert into a double integral by identifying m and n and its partial derivative with respect to x and y. So m is here y by x square plus y square, and n is minus x by x square plus y square. So what is dou n by dou x? Partially differentiate n with respect to x. So by using quotient rule, we'll get x square minus y square by x square plus y square the whole square, as all of you know that. So I can take the denominator square, that is x square plus y square the whole square, denominator into derivative of minus x with respect to x is minus 1, so I'll get minus of x square plus y square in the numerator minus numerator, that is minus x, means minus of minus plus x, into derivative of denominator with respect to x is 2x. So 2x into x already we have, that is 2x square. So I have minus of x square plus y square plus 2x square means 2x square minus x square minus y square. That's what we have, x square minus y square. Similarly, I can get dou m by dou y, differentiate m partially with respect to y, which we get x square minus y square by x square plus y square the whole square. Substitute over here in the Green's theorem. By Green's theorem, this is nothing but the line integral. What we have here is nothing but double integral of dou n by dou x minus dou m by dou y, which we already got. Substitute dou n by dou x minus dou m by dou y. The terms are same, so the integrand is 0, means the integral over R or the region E is 0. So that means the given line integral of f along C is 0. Question number 3. Using Green's theorem, evaluate xy plus y square dx plus x square dy along the curve C, where C is bounded by the line y equal to x and y equal to x square, that is parabola. So again, the curve is a simple closed curve, so we can use Green's theorem. Clearly here m is xy plus y square and n is x square. So find the partial derivative of n with respect to x, that is dou n by dou x is 2x and dou m by dou y is x plus 2y. So I can identify the limit, since we have the curve is bounded by a parabola y equal to x square. Draw that parabola y equal to x square, symmetrical about y axis and having the vertex at origin in the positive direction, and the line y equal to x, that is straight line, passes through the origin. So this is actually a closed curve. Your path goes by this way, OP and then to PO. But instead of that, I can integrate by using Green's theorem, integrate over the region R bounded by this curves. So that means by Green's theorem, the m dx plus n dy, the line integral, is nothing but double integral over the region R. So we have to integrate dou n by dou x minus dou m by dou y. Dou n by dou x minus dou m by dou y already we have taken, that is 2x minus of x plus 2y is nothing but x minus 2y. So this x minus 2y we have to integrate with respect to x and y over the region R. So here I have taken first with respect to y, so taken along a vertical strip. So that limits for y is, the lower limit is on the parabola y equal to x square and upper limit is on the line y equal to x. That's why it is with respect to y, means between the limit y equal to x square to x. So while integrating with respect to y, treat x as constant. Similarly, the outer limit we have to cover from this point to this. So that means x varies from 0 to 1. So corresponding x limits are here 0 to 1. So we have to integrate this double integral, evaluate this double integral. First with respect to y, between the limit y equal to x square to x. So integral of x with respect to y is xy because x is a constant, minus 2 integral of y is y square by 2, that gives xy minus y square. Apply the limit, upper limit is x minus lower limit is x square. So we'll get x square, here x square minus x square minus x square, upper limit gets cancelled, minus of x square into x, that is x cube minus x cube, minus of minus plus x power 4. So plus x power 4 minus x cube. So that's what I have here, x power 4 minus x cube. So integrate with respect to x, outer limit is 0 to 1. So integrate that, integral of x power 4 is x power 5 by 5 minus x power 4 by 4. Upper limit is 1. So 1 minus 5 minus, sorry, 1 by 5 minus 1 by 4 minus lower limit anyhow it gives 0. So 1 by 5 minus 1 by 4 is nothing but minus 1 by 20. So by using Green's theorem, the line integral we have converted in terms of double integral. Only thing we have to find, identifying m and n, find this factor dou n by dou x minus dou m by dou y. Integrate over the region either with respect to y first, x next, what we have done, or with respect to x first. If in case if you integrated with respect to x, then it should be along the horizontal strip first, correct? So upper lower limit is on the line y equal to x means x equal to y, x equal to y to x equal to root y. Then outer limit corresponding to y becomes now y equal to 0 to up to this point means y equal to 1. Both way we can do that. Question number 4. Using the Green's theorem, evaluate integral of y minus sin x dx plus cos x dy, where C is the plane triangle enclosed by the lines y equal to 0, x equal to pi by 2 and y equal to 2 by pi x. Once again, by applying Green's theorem, I can evaluate. So identify m and n. So m is y minus sin x, n is cos x. Dou n by dou x is minus sin x. Dou m by dou y, that is 1, because sin x is a constant, so derivative with respect to y, so we have dou m by dou y is 1. So let me now identify the region. So the region is bounded by these three lines. One is x axis y equal to 0, another x equal to pi by 2, and the next one is a straight line passes through the origin, that is y equal to 2 by pi x. So now your line integral becomes, applying Green's theorem, that is double integral over the region R dou n by dou x minus dou m by dou y, which we have already taken, but only thing is now we need a limit corresponding to x and y. So first either you can integrate with respect to x then y, or y first x next. So I have taken integration with respect to y, so that means along a vertical strip where x is kept constant. So integration with respect to y first means treating x as constant. So I had taken vertical strip where the limits, now the lower portion is on the x axis, that is y equal to 0 to upper portion is on the line y equal to 2 by pi x, and outer limit for x is x from 0 to pi by 2. So apply that limit, x from 0 to pi by 2, y from 0 to 2 by pi x. So I have dou n by dou x minus sin x minus dou m by dou y is 1. So minus of sin x plus 1. So this we have to integrate with respect to y first, next with respect to x. While integrating with respect to y, treat x as constant. So sin x integral with respect to y is y sin x plus y, or I can say it is y times sin x plus 1. Apply the limit, upper limit is 2 by pi x. When y equal to 2 by pi x, it is 2 by pi x times sin x plus 1. When y is 0, it becomes 0. So I have 2 by pi common, you can take it out. Already I have minus sign outside. So I just want to integrate finally x sin x plus x with respect to x between the limit x equal to 0 to pi by 2. So x sin x integration by parts, I can write it as x into first function into integral of second, that is minus cos x, minus integral of second, that is minus cos x, into derivative of x is 1. So minus is already there, minus of minus, so integral of cos x, integral of cos x is sin x. So I got minus cos x plus sin x, and one more term is x, integral of that is x square by 2. Apply the limit. So if I apply the limit for x as pi by 2, then I'll get minus pi by 2 into cos 90. Cos 90 is 0. Sin 90. Sin 90 is 1. 1 plus pi square by, what is that? X square. That is pi square by 4 by 2. Pi square by 8. When x equal to 0, so all the term becomes 0. So simplify that. I can say it is 1 plus pi square by 8 times minus 2 by pi. Problem number 5. Apply Green's theorem to evaluate line integral of 2x square minus y square dx plus x square plus y square dy, where C is the boundary of the area enclosed by the x-axis and upper half of the circle x square plus y square equal to a square. That is circle centered at origin with the radius a. So here also I can, since it is a simple closed curve, by Green's theorem, the line integral I can convert into a double integral over the region R, where the region R is bounded by upper half of the circle x square plus y square equal to a square and the x-axis. So what is m and n? M is 2x square minus y square, n is x square plus y square. By Green's theorem, this line integral I can convert as a double integral of dou n by dou x minus dou m by dou y. N is x square plus y square, so partially differentiate n with respect to x, and m is 2x square minus y square, differentiate partially with respect to y. So that gives here n with respect to x is 2x, partial derivative of m with respect to y is minus 2y, minus of minus plus 2y, so 2 times x plus y. So this is what we have to integrate over the region R bounded by the semicircle and the x-axis. Now if you integrate with respect to x first, y next, or y first, x next, then either you have to integrate along a horizontal strip between the limit minus root a square minus x square to root a square plus minus x square, or if you take with respect to y first, then along a vertical strip, that is 0 to y is equal to square root of a square minus x square. So instead of that, as you know, whenever a region is bounded by a circle in full or half, we can convert it to polar coordinates. So changing into polar coordinate, that means substituting x equal to r cos theta, y equal to r sin theta, and dx dy r dr d theta, and corresponding limit for r and theta, as r varies from 0 to a, that is radius of the circle, and theta varies from 0 to, so it is a semicircle, so that's why it is 0 to pi. So I substitute the limit 0 to pi for theta, r equal to 0 to a, x is r cos theta, y is r sin theta, r common, you can take it out, dx dy r dr d theta, that is r square dr d theta. Now it is constant limit, so that the function is also separable, so you can split this into two simple integrals. One is with respect to r, function of r is r square with respect to r between the limit 0 to a, and function of theta is cos theta plus sin theta with respect to theta between the limit 0 to pi. Integral of r square is r cube by 3, apply the limit 0 to a, and integral of cos theta is sin theta, integral of sin theta minus cos theta. If I apply the limit theta equal to 0 to pi, upper limit sin theta for pi as well as 0, it vanishes, minus of cos pi is minus 1 minus cos 0, that is minus 1, minus 1 minus 1 minus 2, outside I have minus, so it gives a 2 into 2a cube by 3, that is 4a cube by 3. So we have taken the problems on Green's theorem that relates the line integral into a double integral over a region R bounded by a simple closed curve C. In the next video session, we are going to take Stokes theorem and Gauss divergence theorem.